Good day, everyone, and welcome to our webinar presentation. My name is Adam Harris, CEO from C-Therm Technologies. Very pleased to welcome you to today's webinar. Today we take an application focus on looking at bedding materials. The title of today's presentation is on quantifying thermal performance in bedding and how specifically effusivity helps improve your sleep. In a couple of minutes, I'll be introducing the star of the show, Arya Hakimian. He's an application scientist and leader here at C-Therm Technologies. He's worked with a lot of clients in the textile space. He's been collaborating with a special research project with folks from the University of Oregon and worked with a number of top textile apparel producers in the world. So very grateful to have Arya Hakimian on the line with us today. He's curated a great presentation specifically on bedding materials. I'm the warm-up act, so I'm going to provide just a little bit of quick background on who C-Therm Technologies is. See a lot of familiar faces on the line with us. Great to have you with us. Some folks that are maybe new to C-Therm and might benefit from a little bit of background information on who we are. So C-Therm Technologies is a world leader in characterizing touch properties. We patented a special method described as the modified transient plane source technique, which became an ASTM standard, a global standard that was generated through consensus among many of the top brands active in this space, really defining a consistent way to how we're going to characterize performance from a sense of touch. So that means specifically quantifying warm feel and the inverse of that, which is cool touch, very applicable when we talk about bedding and keeping you comfortable, how important that is when we sleep and impacts the quality of sleep. And this is something that is a unique niche area that C-Therm really excels at. Our organization is a Canadian tech company based on the East Coast. We support a wide range of applications in the area of touch performance, from wearables, bedding, performance textile, consumer goods, automotive interiors, and building materials. Wherever human touch comes into contact with materials, those materials may consider the touch property a critical performance attribute, whether that's the tiles you walk on and the bathroom floor, or whether it's the automotive seats in your new SUV, or the sheets on your bed, the mattress, the pillow, your pajamas, and so forth. Touch has a remarkable impact on our perception and our experience in the environment we have. So a very important property, and really important to be able to quantify it from a performance perspective. I'll offer just a quick overview of our product lineup just to provide a bit of an orientation here. We're really focused on the product on the right in this discussion, and this is not a heavy a product focus in today's presentation. It's really more application oriented, it's educational in nature, but you will see some results presented, and those results were generated with the TX Touch Experience platform, which has the MTPS sensor operating to ASTM D7984. So that's the product on the right-hand side you see there. In the middle, we have our Trident product. This is our most popular product. It's a research-grade instrument for measuring thermal conductivity primarily, but also can measure effusivity, but offers a broader mix of sensor capabilities, including the TPS Flex sensor, which offers specialty for testing thin films, anisotropic materials. You can envision how that could be complementary if you're working with coatings and multi-layered structures in a textile advanced application. So there might be something of interest there. We do have some other webinars coming up and that are previously also recorded on the Trident system. I know in November we have a webinar looking at thin film characterization with the Flex TPS. So that's an option, and certainly something we're happy to provide you more information on if of interest. And then on the far left, we have our TC kit. And the TC kit is our most economical offering. It's really about offering clients an opportunity to get into the game of measuring thermal conductivity. It does not measure thermal effusivity, which is what we're really focused on today. But there is a lot of lap over in those thermal properties, and often folks that are interested in one also interested in the other. And so just a little bit of opportunity there to present some awareness on, with the TC kit, you've got a very low cost opportunity to generate some very good thermal conductivity results. Suitable for materials up to about 65 watts per meter Kelvin. Used a lot in academic research where budgets might be more of a constraint, or in organizations that are just trying to get off the ground, bootstrapping a very basic R&D effort. This is a nice opportunity to establish some capability. We won't talk much more about the thermal conductivity side. Today, we're really going to zero in on touch and the importance of quantifying touch in the application of bedding materials. So as I mentioned earlier, you'll see some featured content with results from the TX system. This system can operate across a broad range of temperature, humidity, different environmental conditions. There is a compression test accessory that I know Aria is going to detail further in terms of the importance of that accessory. If you compress a textile or fabric, it's going to alter its thermal properties, and it's important to really understand that and have a consistent means of reproducing that measurement. So I've reviewed some of the slides with Aria before and gotten some insight in terms of the content he's presenting. I know there's a considerable discussion on the CTA and its usage, and you'll learn more about that shortly. But in summary, the TX system operates according to D7984. It is the only system that satisfies the full requirements of that standard, most notably the importance of the guard ring, which I believe Aria is also going to detail in his section on the theory of operation, how that ensures a one-dimensional heat transfer into the sample, which is so important from the aspect of measuring thermal effusivity. The precision better than 1%, accuracy better than 5%. This is really designed for lab quality control and can be applied also in at-line testing in some application areas. This is just a close-up view of what that sensor looks like. You'll get some further detail here later on how it operates, but it is essentially a single-sided sensor. The sensor is heated electrically, and at the same time, we're monitoring the temperature change over time. This is inversely related to the thermal effusivity of the material. It is a fully liquid-proof sensor. The red ring that you see that goes around the green main chip, that is an RTV silicone that seals the sensor and makes it fully liquid-proof. So suitable for 100% humidity. We've had folks test neoprene dive suits and other fully saturated textiles. So water is not a problem. And this is one of the benefits of the transient technologies. These are all external sensors, so they can be incorporated in a wide range of environments, including some of C-Therm's unique high-pressure cells, which allow for testing at elevated pressure and temperature and all kinds of control options on the atmosphere. If you're looking not so much to invest in a system, but you're looking to have a service completed in characterizing some of your materials, the TX system is available at the top textile labs around the world, notably Bureau Veritas in the US and Asia, the Taiwanese Textile Research Institute, the Intertech Taipei facility, Group CTT up in Quebec, PMIC on the west coast here of the US, Axle Products. All of these top testing facilities offer the testing capability with C-Therm's TX system and fully meet the ASTM compliance necessary in offering that test service. Just like to, before I pass it off, just offer a brief comment from a customer of ours on the TX product. This one's from Dr. Christian Haid at Adidas. He's in their apparel intelligence group, which I understand is their futures group, looks at products that are about 3 to 5 years out from coming to market. Really a nice, succinct, very to the point quote from Christian, which we're very appreciative of, just says the device is working perfectly. So we thank Dr. Hyde for that comment. And AJ, if you could maybe drop in the link, just the webpage where you can look at other client testimonials if you're interested in learning more about the typical customer experiences. There's a page with 50, 60 plus different client testimonials. It's an interesting review of and getting a sense of who's using the equipment, how are they using it, and so forth. So worth checking out. All right, I'm going to stop sharing my slide deck and I'm going to introduce the star of the show now, Arya Hakimian, an application scientist with C-Therm Technologies. Some of you may have met Arya on client consultations. He runs our virtual demo facility. He works very closely with clients in support of helping them understand what are the best types of methods to select for their types of materials, because there are a variety of options depending on the scenario. Just a great guy all around. So very pleased to introduce Arya. And at this point, Arya, I'll drop off and rejoin you for the Q&A session.
Awesome. Perfect. Thanks, Adam. Hello, everyone. So nice to be with you all here today. Just to get the slides set up here. Alrighty. So as Adam mentioned, we'll be going into a little bit of a deep dive on effusivity as it really relates to sleep and different types of bedding materials, fabrics, textiles in this space. So just a quick introduction of why are we looking into this, and why is sleep so important? As most may be aware, it's sleep is really what recharges our body. It gives us that the energy to keep on going. Gets us ready for the next day. On average, you probably heard the rule of getting 8 hours of sleep each night. A lot of the times, this may not be a really realistic criteria for some people. And there can be a multitude of factors that come into play here as to why that can be challenging. And we'll be kind of addressing some of those here today. A few just quotes pulled from some various studies across some different journals over the past few years, really just highlighting the fact that one of the main components to getting a good night's sleep is making sure you're at a comfortable temperature. You kind of see throughout, excessively high or low temperatures can really be detrimental to optimal sleep. These non-ideal temperatures have been associated with higher use of hypnotic medications in some regions. Even certain studies even looking at the changes to climate, how the overall increase in nighttime temperatures can result in some sleep deprivation issues. But ultimately across all of these studies, it's very obvious that the temperature at which we're sleeping at and the environment that we're in are highly related to how well we're going to be able to sleep throughout the night. So, kind of doing call it a bedtime material breakdown. When you're sleeping, you may have things like blankets, sheets, pillows, you have your PJs on. These are all things that are going to be in direct contact with the human body. Most will be sleeping on a bed or mattress of some kind. Here we see an example of a memory foam type structure where even the mattress itself has different internal components, different layers that all build out that base. So as you can see, there's a lot of different materials here, different sample types to consider when you're looking at that overall thermal aspect to your sleep environment. Now, how are we going to go about quantifying these performance of these materials, and how do they keep you cool? So, the thermal interactions between the body and the materials that you're in contact with are really going to be a key aspect to regulating your temperature. And, amongst some of the many factors to consider, thermal effusivity, which is what we'll be focusing on here today, is really the dominating factor that dictates thermal interactions upon contact. So a little step back for those that may not be familiar. What is thermal effusivity? So effusivity is sometimes referred to as thermal inertia. Really, it defines a material's ability to exchange heat with another body that it's in contact with. You can see the units displayed there for effusivity, but really this is describing you have two different materials coming into contact and defining that interaction that can occur. You can determine things like the interfacial surface temperature, so the temperature that will be created when two materials of different effusivity at different temperatures come into contact. This can be applicable for two different types of kind of materials, whether it's foams, textiles, polymers, metals, really across the entire range there. Effusivity can be an important factor, but we're really looking at it from the perception of when the human skin, or you see in the example there, a hand is coming into contact with a different material, and what that perception is felt. If you've been on any of our previous webinars or seen some content, this is a graph that we like to show. It just kind of details the warm feel, cool touch aspect that can be determined based on a material's thermal effusivity. So as an example, on the lower end, you see around 100 and below. These fleece type samples may be warmer feeling in nature, whereas you push that to the upper limit into the the 200-300s. You get into different cottons, different leathers, different coatings. These can all yield more cool touch. And then on the far right there, you'll see water is anchored at the upper end, so you can get into the analysis of these semi-saturated textiles and materials as well. Now, effusivity, again, this is really coming into claims validation for certain groups. We've seen this being used across different industries, and here are just some examples of how effusivity can be used. So groups are making claims such as, keeps you cool to the touch. Effusivity is one way that you could go about quantifying that, and an option there for whether you're looking at product development or further along down the chain, such as here when you're looking to make those types of marketing claims for advertising. And all of this, we'll be focusing on the measurement through the modified transient plane source, or MTPS, which Adam had detailed earlier. Kind of a few notes: it provides both thermal conductivity and thermal effusivity measurements. It's the only method that conforms to ASTM D7984, and we'll get into that into a little bit here. And really, one of the main benefits of the MTPS and really transient methods in general, it allows for more representative testing conditions. So a couple examples: humidity, temperature, pressure. These are different factors that can and will influence these types of thermal measurements, and being able to fine tune your testing geared towards the most representative conditions are going to give you the best possible results for your specific application. So not to dive too deep into the theory today, but more of a high-level principles of operation. The way the measurement works, first off, a known current is applied to the sensor's spiral heating element. This is on the top side of the sensor chip, and this results in a temperature rise at that sample sensor interface. You can see in the image on the right, what the software is going to be doing here is monitoring that change in temperature that occurs as a function of time, and the differences in thermal response are what's used to get at these thermal effusivity and conductivity properties. Now, one thing to make note of, and this really does differentiate the MTPS from any other transient measurement technique, is what's referred to as the gartering. So the gartering goes around the circumference of the sensor coil, and what it does, it helps support a one-dimensional heat transfer into your sample. So during the initialization of the heat pulse for your measurement, the gartering will initialize simultaneously. And then as far as the measurement zone is concerned, it prevents any of that lateral heat spreading from occurring. Last note, these are based on factory calibrations that are applied to the sensor. For us here today, we'll be focusing in on those cals that are used for, again, fabrics, textiles, foams, things like this. But there are various calibration types available for a multitude of samples, again, going into liquids and powders, metals, which is outside the scope of today's presentation, but those are available. Okay, so with the background in place, really for the remainder of the session here today, we're going to be going through a few different application highlights, pulling from a few different fields, but all within the realm of thermal effusivity and how that's going to be important with respect to the specific applications. So starting out, just wanted to give a little bit of a kind of an example of some standard ASTM D7984 testing of fabrics. Again, so this method, the standard test method for the measurement of thermal effusivity of fabrics using an MTPS instrument. So as written, really, this standard provides a lot of guidance on the setup requirements, your overall parameters that you need to use for the measurement. You can see in this little graph here, you have the different components. You have your laptop connected to your controller device, which then feeds into the MTPS sensor, and in this example, inside of a compression device with the sample layered on top. So fairly simplistic setup that we're looking at here, but there are various factors that you need to consider for your testing. To conform to the standard, there are certain things, certain criteria that you need to meet, such as temperature, relative humidity of your test environment, and the conditioning of the samples. And there are other things as well, but really taking note of temperature and humidity are going to be among some of the most important aspects to consider, especially if you are looking to do comparison of these types of materials with other groups and things down the line. So here we see an example setup of testing some textiles. So fabric materials are draped over the MTPS sensor, and the little pressure foot that you see on the top side there is connected to the force gauge of the CTA. So that's kind of what your setup will look like. The CTA is used to apply a consistent force load on the top side of the sample. As I mentioned, the MTPS has various calibrations depending on the material type that you're working with, and some of which are dedicated specifically to these fabrics, textiles, and installations. And then ultimately your sample is placed on top of the sensor and compressed. The standard does require a minimum test thickness of 1 millimeter. So in the scenario where you may be dealing with a very thin fabric, there's a layering technique that can be done, somewhat detailed in that picture on the right. But that's just kind of a general example of a setup. Walking through a few different kind of data sets that were collected, trying to fine tune it here for some applications towards sleepwear. So, your PJs that you may be wearing during the evening time. The data here, this is all pulled from the study I believe Adam mentioned that we are working with the University of Oregon on this perception analysis. This is some of the initial data that was taken from the MTPS measurements, all of which were compliant with the standard D7984 test conditions. But just looking at the data here, just want to highlight kind of two different sections. We have the data in red on the left, so your warmer feeling materials, so your thermal fleece cotton blends. This is the type of fabric that you may be taking out maybe this month as the winter starts, or the fall winter months start to approach, gets a little bit cooler outside. You need something a little more warm feeling and cozy to keep you comfortable. And then on the right side, you can kind of see those higher effusivity values coming in. So 100% cotton, a cotton spandex blend coming in at a much higher effusivity, approaching more of that cool touch fabric. Again, these may be some of the materials you're putting away until next summer, as sad as that is to say. But the story you may be able to see here is the thermal fleece on the far left, obviously coming in at the most low number, the lowest effusivity result. Taking a look at the cotton t-shirt again, about 3-4 times higher in effusivity. But then you can see the fleece cotton blend, not quite in the middle, but understanding here that the different mixtures of materials in these types of components can result in obviously different thermal responses. And by understanding how general materials will result in these types of measurements, you can again fine-tune your construction, your blend, to control the desired properties of interest. The highest effusivity measurement that we're reporting here is the cotton with the spandex blend. And I will note the spandex component of that sample, it was very low, it was maybe about 1 or 2%, but compared to just a pure cotton, again, showing that net increase. So a few different examples of how you can use these effusivity values to fine tune and control the desired properties for your specific products. Up next, taking a look at the influence of compression. So certain materials may be more compressible than others, but as a general rule, if you're applying any amount of force on the top side of a sample, this is going to result in a decrease to the thickness, resulting in an increase in density. This leads to a net decrease in thermal resistance, and finally that results in an increase to your thermal conductivity or thermal effusivity measurements. And the reason for this, essentially, if you kind of take a close-up look at, in this example, this filled fiber type sample, you're going to have these individual strands or loops of fibers interdispersed with these different air voids. And if it's uncompressed, there's obviously going to be much more air present. Air is a extremely good insulator, and therefore the more air that is present in that measurement zone, that's going to result in a much lower effective measurement. If you compress and densify that sample, you're moving that air out and away from the active area. Therefore, this is how you're getting at those higher thermal properties. And we'll take a look coming up at a quick data set that was collected on a compressible foam here. So in this result, or in this study, we tested the sample under varying force loads from 50 to 500 gram force. The calibrations used had a 3-second measurement duration. This is really good for most of those foams and insulators that may be a little more dense in nature. And the environmental conditions, again, always good to take note of those. Temperature is approximately 21 degrees Celsius and approximately 45% relative humidity for this test. And what we're seeing here, taking a look at the effusivity results, is essentially what we were expecting. The increase in effusivity as a function of the applied force or the compression. So ranging from 50 gram force resulting in the lowest value, with 500 gram force being the highest. Now, I have this straight line showing that net increase. In reality, if you were to sample many more pressure points across a wider range, you will start to run into areas of diminishing return where maybe at the low end you see a very little effect. As you increase that force load, it starts to dominate the measurement, and then maybe at the upper end, again, you hit that point of diminishing return where the sample is just really approaching a fully compressed state. But this will really vary depending on the type of sample, obviously the density of the material, the composition, in textiles and fabrics, even the weave and the pattern, the structure that is used. These will all have an influence on how they measure with respect to thermal effusivity and how those measurements will change as a function of, in this case, force. So this next example, some considerations for a multi-layered structure. Recalling back to the image we showed a little bit earlier. A memory foam mattress may have these different layers and internal structures to them. Of course, additional components we're not looking at here today. Maybe the pillows, the blankets. Again, you can get into some very complex, call them micro environments that you need to model and understand. But just taking a look at the foam layers here, one thing that you can do is if you're looking to get that, that pure effusivity measurement, really taking the measurement of the individual layers, what many groups that we work with do, and then take those values, whether it's the effusivity, the conductivity, and use that in different modeling softwares. I believe Adam mentioned, but we actually do have a talk coming up on in November about how some of this thermal data is used in some of these modeling programs. I believe it relates to polymers more so, but still interesting to see how that data is used. But again, really taking the individual materials, understanding their thermal properties, and then using that to construct the most ideal sample or product that you're looking to develop. Now, of course, there is obviously interest in testing a multi-layered system and kind of understanding how that can play out if you do have different layers. You do need to be understanding of how the method assumes there are certain assumptions with the method with respect to layered structures and how that heat pulse will propagate through these materials. But to do these types of studies and this kind of more research and development application of simulating contact duration, we can get some very interesting results by doing different studies of the effective probing depth as a function of test time. And in this example here, we're looking at a structure that has a textile fabric on top of the foam. This is the same foam that we showed data for a few minutes ago, but we'll take a look at how varying the test time can give you some interesting results and may tell you a little bit about the sample that you're looking to work with. So test conditions, again, most of the results that were taken for today's webinar done at about room temperature, 45% humidity, 500 gram force compression. On the left, you can see just the individual materials model or the measurements that were taken. So the foam coming in just shy of 50 effusivity units, with the fabric being about 125 or so. Now, if you look at the graph on the right, what was then done is taking that foam fabric stack and using calibrations of different duration, which is essentially going to probe to different depths into the material. What we're seeing here is as the test duration increases, you're getting more of a representation of an extended contact and a different probing depth through those layers. So that initially higher effusivity top surface is being more and more influenced by the foam on the underside as the measurement duration increases. And this may give you some very interesting data with respect to how you're stacking the samples, the thicknesses of those top layers and how the bottom layers are influencing and interacting. And again, just different things that can be done, again, all with the MTPS sensor, just by modifying the different test conditions that are used for your measurements. What if the material is homogeneous though? So just as a note here, the data that I just presented, that was on a sample which had 2 distinct layers, and you kind of see the different properties as the probing depth changed. But if you took a homogeneous material, this is on a type of foam, in this case it was a rigid LAF type foam, using the calibrations for that material type, but with different test durations. Again, if it's homogeneous, there's no layered structure to it. You can see very comparable results, essentially no difference based on the sample that is tested. So again, understanding what type of sample you're testing and how you're testing it is going to be really important to really pull out those bits of value that you're getting from these thermal measurements. All right, up next, this is a type of application that we've seen across quite a few industries, not just in the textiles fabric space, but PCMs as a form of a coating or a filler, really interesting topic. If you're not familiar, a PCM or a phase change material, essentially it'll undergo a transition with respect to a thermal introduction. So first in its solid state, if you introduce a temperature to it, the PCM starts to absorb that thermal input and begins to melt. enters into a liquid state, and then if you were to that temperature was to decrease, the opposite happens. So the PCM begins to solidify, releasing that thermal input to the environment. It goes back into the solid state. So PCMs are a very interesting class of material. There is a lot of thermal properties to consider with this class of sample. Effusivity, conductivity, amongst heat capacity as well. These are very important properties to understand with respect to PCMs in general. But when we're looking at applying them to fabrics and textiles, that's where the effusivity really comes into interest. This data that we're presenting, it's data we've had collected a few years back, but it's a really interesting application work that we did with partner, friend Wim he's the founder and CEO of Colortex. They were developing these various PCM coatings for various textiles and fabrics. And what they were looking to do is essentially create these next generation fabric cooling technologies by incorporating the PCM onto the top surface of the sample. Now, while subjective, if you've ever touched a sample that has a PCM on it, there's no denying that there's going to be some amount of cooler feeling to it. Some of these foam type samples, clothing that have PCMs, if you can touch a control and touch the test sample, just by the sheer contact with your hands, you can really pick up on those differences. But we need some way to quantify that, and these groups need ways to quantify that to really help market and again prove that there is some benefit. So this is all coming back to the effusivity measurement. Just taking a look at a couple different samples, so an interlock fabric and a non-woven, both treated and untreated. And across both cases, there was a notable difference in thermal effusivity from the control to the treated sample. In this specific case, ranging about 35 to 55% increase between the two. And again, this is just one way that you can use this types of data to back up these types of claims that are being made, especially if before you're relying on taking these different samples and showing them to different clients and groups, getting them to touch it and experience for themselves, with the travel restrictions that may be in place in the different regions of the globe right now. This really comes into a savior, really being able to show these quantitative numbers to back up those types of claims that you may not be able to get in direct contact with some folks. All right, and then weighted blankets for improved sleep. These weighted or gravity type blankets, originally used as a therapeutic tool for individuals with autism and mental health conditions, really have become popularized in recent years. If you've seen them advertised on various social media as a sleep aid or a way to help reduce anxiety. I believe some of the main consensus is the weight of them help mimic being basically hugged or giving you that comfort feeling. Now, the scientific data behind the efficacy of these blankets is, say, it's out, inconclusive for right now. But that being said, they are popular. There's a multitude of brands out there that offer these types of materials and products. We took a look at one of them, and specifically here looking at one of the optional add-ons they provide. Many groups and companies offer add-ons, and in this case it was a cool feel cover. But we wanted to see, does that really provide any value? So you can kind of see the structure of the weighted blanket there in the middle. It's as a fabric outer layer, an insulation on the inside, and then some type of weighted sample, in this case of these small glass beads. And they can be constructed in different ways, different designs, even different materials used. But the main idea is, again, you have a blanket that has this insulation and added mass to it, adds a certain weight on top. But you can imagine that may add some additional insulative properties with that warmer feel. So does the cool blanket cover provide any value for this type of product? Well, through some of the testing that we've done, it showed that there was quite a significant difference in thermal effusivity from that outer surface cool blanket compared to the weighted blanket itself. About greater than 75% more cool feeling with respect to that add-on. Now, of course, you have to weigh the cost differences between some of these add-ons from different companies. But again, this is just one way that you can make claims and back up those claims to really prove why this specific product or add-on is going to add value to your end user. And in this case, again, showing quite a significant influence here. So we've gone through most of today's presentation, again, really focusing in on thermal effusivity. But what about thermal conductivity? It can have certain applications for these types of products and industries. Just to quick background on it, thermal conductivity really defining the rate of heat flow through a material across a temperature difference. Again, not really used to describe that touch perception property, but again, more so the heat transfer through the bulk. Thermal conductivity broken down into units of watts per meter Kelvin. This is based on watts are coming from that thermal input across a given thickness of units M for meters, and again across a temperature differential in Kelvin. So that's how we get your units of watts per meter Kelvin. Just as an example data set, you can see similar to the result that I showed earlier based on effusivity, performance in conductivity can also be tested or mimicked as a function of compression. Again, this is another data set collected with the MTPS using the CTA, taking this compressible lofted sample. I believe this was an insulation type material. And it was applied or tested under different force loads. And looking here at the sample thickness being indicative of the force. And you can see as the compression was at its highest point, so at the far left, this resulted in the highest effective thermal conductivity. Again, because you're pushing out that air, having more of that material contact, adding better pathways for heat conduction to occur. Then as you go to a lower and lower sample thickness, a lower compression state, again, that result starts to decrease. But here you can see that initially it was very high, and then it dropped quite steeply, and then it began to flatline a little bit near the end there. So again, kind of looking at those, call them points of diminishing return. This is really good to know that there may be certain cutoffs where further adjustment of the, let's say, compressive load or the density of the bulk sample may not result in any significant improvements, except for those that may be on the very minor scale. So just some, again, further examples there. Again, all with the MTPS, but in this scenario, looking at thermal conductivity. So just finishing up, there are a few frequently asked questions kind of related to this space that I did want to just highlight here today. These are questions that do come up quite a bit when we're talking about these different types of bedding, foam, insulation industries. Thermal resistance, R value, RSI. These are questions that we get a lot, like what are they, what do they mean? So thermal resistance, noted as R, this is an object property dependent on the material's thickness. So R can be calculated by dividing the thickness of your material by its thermal conductivity. Now, R value and RSI, they're just different ways of expressing the same thing. They're all thermal resistance. One is simply imperial, or the other one is the metric system, just different forms of the same type of reading. In both cases, though, a higher value of thermal resistance means a better insulative performance. And the reason why this may have some application here, the picture on the right, that's a sleeping pad. So if there's any outdoor folks here, go camping quite often, sleeping pads can be placed below the sleeping bag, and they're generally denoted in quality by their R value. So there are certain industries where, again, this is a type of, call it sleep related device where the thermal conductivity, the thickness, that thermal resistance are going to be coming into play. As a note, to convert between RSI and R value, you simply, taking the RSI value and multiplying it by a constant, you can swap back and forth between the two. And again, just a question that we do get somewhat, so wanted to detail that for you here today. One of the other ones is taking a look at these two other types of values, CLO and TOG, so CLO, TOG. These are units that are unique to the textile fabric industry. Again, here, they're just simply alternative ways to represent thermal resistance. 1 CLO is essentially the amount of insulation that's needed for a person to maintain thermal equilibrium 21 degrees Celsius. CLO is used a lot in the, again, clothing industry, where essentially if you take the human body without any clothes, you're at a CLO value of 0. As you start adding individual garments, this can increase your overall CLO. So kind of see the 3-piece suit there. You would take the shirt on the underside, the vest, the suit jacket, add up all of their individual CLO components to get the overall CLO value for that dress or that clothing. Now, TOG, this was developed as a easy to use, essentially alternative to the SI units for thermal resistance. TOG is used largely, you'll see it used for certain duvet, kind of those thicker, warmer blanket type materials. And again, it was just kind of an easy way to get around dealing with units of meters squared Kelvin per watt. Essentially, you can see there's the conversion factors down there, but 1 CLO equals approximately 1.55 TOG, and that equals just 0.155 meters squared Kelvin per watt. So again, just these are certain questions that you may run into, or if they ever come up in discussions with your individual groups, they may just be different ways of looking at things such as thermal resistance, which again can all be related back to the thermal conductivity of the sample related to its overall thickness. So just wrapping up here is a few conclusions. Thermal effusivity, really describing the dominating factor for heat transfer between two bodies in contact. The MTPS is the only method that conforms to the ASTM D7984 standard. This really comes back to certain aspects of the way the sensor is designed, the gartering, all very important aspects to consider. D7984, it's been globally adopted since around 2016 to quantify performance of these types of materials across industries for material selection, R&D applications, QA, QC, and as we mentioned, claims validation being among some of the most used areas. Ultimately, testing the individual components or even the layered structures can be useful for these developmental purposes. Again, just keeping in mind that the type of sample and your overall setup, taking note of the material type, the thickness, temperature, relative humidity, all those aspects, being able to fine tune those and control them are going to give you the best chance of getting those good, accurate, and representative test data. And the MTPS really provides users, again, with the ability to easily test thermal effusivity and conductivity across a range of material types. So whether you're dealing with thinner fabrics, foams, insulations, the MTPS, depending on what you're working with, is able to go through and handle all those different materials for you. So wrapping up here, I know there's a few minutes left on the hour. Just want to say thank you for your attention here today. Again, my name is Ari Hakimian. You can see my email on screen there. If you did want to reach out, I've had some great discussions offline with certain folks through these webinar connections. AJ just posted my LinkedIn profile there. Feel free to reach out if you did have any questions, and always happy to continue those discussions. Just as a note, additional resources on our website. There's an extensive webinar library where you can find past recordings as well as this one featured, as well as a tech library. Lots of different application notes, publications as they may relate to the materials that you're working with. So a great option to check out there. If you were interested in taking a next step, whether that's booking a video demo or a call with us, getting a complimentary sample testing with respect to moving forward with an instrument, or even just requesting a quote, again, definitely feel free to reach out. You can see the contact information there. I will note the video demos are something that we've taken strides in developing over the last year and a half, with the lack of ability to do these travel. If you really wanted to get a better idea of how you set up a sample, seeing how the software takes the data, how that all plays out, these video demos are a great way to do that. We basically book a session, it's about 30 to 60 minutes, and we can go through quite a few different applications and sensor types as needed for your applications. And finally, just plugging some upcoming webinars. There is one coming up in a few weeks, October 21st. We'll be introducing a new high temperature TLS sensor. This is going to be geared towards thermal conductivity of polymer melts. If you have interest in injection molding, different 3D print technologies, or polymers in general at high temp, this may be a great resource to take a look at. Following that, later in the month of November, we have the importance of thermal conductivity and XEV thermal management modeling. This is going to be presented alongside our guest speaker, Dr. Zachary Edel, in partnerships with Thermo Analytics. And again, this will be coming up a little bit later in November. AJ's been posting these different links in the chat there. Feel free to take advantage and take a look at any of those as you see fit. So I'd like to thank everyone again. I'll pass it back to Adam as we wrap up the session and enter into the Q&A portion.
Excellent, Aria. Great job. Really interesting content. I love the work on looking at the mattresses and different bedding materials. Some great results there. Very appreciative and grateful for your efforts there. We have a short survey that AJ is going to, I think, drop in the chat box. It should only take 1 to 2 minutes, I think, to complete. It just helps us understand how we're doing in terms of generating this content. If there's ideas you'd like to see focused on in the future, bit of an opportunity to weigh in here. You can also use the chat box to provide any comments or feedback on how today went from your perspective. But at this point, we're going to move into the Q&A session. So if you're able to stay on the line for the Q&A session, that's great. If you have to jump off, that's okay too. And I just want to express our gratitude and appreciation for you joining us today. I hope it was an interesting hour spent talking about effusivity's role in improving sleep quality. And we certainly would be happy to pick this conversation up one-to-one if you would like a private consultation or look to schedule, perhaps a virtual demo or anything of that nature. We're certainly here to help. So pleased to do so. Wish everyone a wonderful afternoon. Otherwise, I'm going to stop the recording at this point and we'll open up the Q&A session.